Right now, something metal is within arm's reach of you. A zipper, a doorknob, the frame of your phone. You touch metal so often you've stopped noticing it. Cold, hard, permanent. It feels like it was always just there, waiting to be picked up. It wasn't. For roughly 200,000 years, Homo sapiens lived without touching a single piece of refined metal. Then, sometime around 9000 BCE, at a site called Sayonu Tepesi in what is now southeastern Turkey, someone picked up a reddish-orange rock that didn't behave like other rocks. It didn't shatter when struck. It bent. That single moment, a person noticing that one stone was different from every other stone, is the beginning of a chain of accidents that would eventually put a metal rectangle in your pocket that can talk to satellites. Here's the disruption. Ancient humans didn't invent metal. They stumbled into it repeatedly over thousands of years, almost entirely by accident, and the order in which they found each metal was dictated not by intelligence, but by geology and luck. This is going to change how you think about invention itself. You probably picture discovery as a genius moment, an individual figuring something out. The real history of metal shows something stranger. Technology advancing not through insight, but through people noticing that fire, mistakes, and shiny rocks kept intersecting in useful ways. Start at Sayonu, around 7000 BCE. Archaeologists excavating the site in the 1960s and 70s found small beads and pins made of copper, but copper that had never been melted. This is called native copper, copper that occurs in nature as a pure metal, not locked inside ore. It's rare, but it exists in visible nuggets and veins, sometimes bright enough to catch light on a hillside. Early humans treated it like an unusual stone. They didn't smelt it. They hammered it cold, the same way they shaped flint, using pressure and repeated blows to slowly change its form. Over hundreds of years, sites across Anatolia and the Fertile Crescent, Ashukla-Hoyuk, Çatalhöyük, show more and more of these cold-worked copper objects. Beads, awls, small hooks. There was no metallurgy yet. No fire involved in the transformation. Just people repeating a physical action, not striking a stone, and discovering that this particular stone didn't crack like the others. It flattened. It could be reshaped without breaking. For nearly 2,000 years, that's all metal was to humans. A slightly strange rock that bent instead of shattering. But here's where it gets stranger. Around 5000 BCE, at a site called Belivode in modern-day Serbia, something changed. Archaeologists led by Miljana Radivojević, publishing findings in 2010, found copper slag, the waste material left behind when copper is extracted from ore through heat. Not native copper, smelted copper. This is a completely different process, and it likely wasn't figured out on purpose. Here's the leading theory. Neolithic potters were already building kilns that could reach temperatures above 1,000 degrees Celsius to fire ceramics. Kilns lined with malachite and azurite, blue-green minerals that were prized as pigments and decorative stones. Some of these mineral-rich rocks happened to be copper ore. When they sat in a hot enough kiln, surrounded by charcoal, a chemical reaction occurred. The charcoal pulled oxygen out of the ore and liquid copper separated out and pooled at the bottom. Someone, one day, opened a kiln expecting broken pottery and found a puddle of metal instead. That accident required an extremely specific set of conditions. Ore rich enough in copper, a kiln hot enough to reach smelting temperature, and enough reducing atmosphere, meaning low oxygen, high carbon, for the chemical reaction to run to completion. Radivojevic's research suggests this happened independently in multiple places across the Balkans and the Near East, within a few hundred years of each other, which tells you something important. This wasn't one genius. It was thousands of people running the same accidental experiment, firing colorful rocks in hot kilns, until somebody, somewhere, got the right combination. Once smelting was discovered, everything accelerated. By 4500 BCE, the site of Pločnik, also in Serbia, shows evidence of copper smelting on an industrial scale for its time. Furnaces, slag heaps, and finished tools including chisels, hooks, and axes. Copper stopped being a curiosity, it became infrastructure. But pure copper has a problem. It's soft. A copper axe blade dulls fast, bends under pressure, and won't hold an edge the way stone tools can. For over 1,000 years that limitation stood, until someone, somewhere, started mixing copper with something else. That's not the whole story. The next accident happened for the same reason as the first one. Mixed rocks, hot fire, no idea what would come out. Early smelters weren't working with pure copper ore. Real deposits are often naturally contaminated with other elements, and one of the most common was arsenic. When copper ore containing arsenic was smelted, the result was arsenical bronze, a metal harder than pure copper, easier to cast, with a silvery sheen. Sites in Iran like Tal-e-Iblis show arsenical bronze production as early as 4000 BCE. For centuries, smelters likely didn't know why some batches of copper came out stronger than others. They just knew certain ore sources produced better metal, and they returned to those sources. There was a cost. Heating arsenic-bearing ore releases toxic fumes. Some researchers, including archaeologist Charles Pigott, have proposed that repeated arsenic exposure caused nerve damage in smiths working these forges, and that this may be part of the origin of the limping, lame blacksmith figure that recurs in mythology, from the Greek god Hephaestus to the Norse Wayland the Smith. If true, the myth is a folk memory of an industrial disease, encoded in story because nobody had the chemistry to explain it directly. Then, sometime around 3000 BCE, smelters in the Near East and the Aegean began deliberately alloying copper with tin instead. True bronze. Tin bronze was stronger than arsenical bronze and didn't poison the people making it. But tin ore is geologically rare and almost never found near copper ore. The nearest major tin sources to Mesopotamia were in Anatolia and later as far away as Cornwall in modern England and Afghanistan's Badakhshan region. Bronze Age trade networks, some stretching over 3,000 kilometers, existed largely to move tin to copper. Bronze became the defining material of an entire era for a simple reason. It was the best metal humans could reliably produce for almost 2,000 years. And it stayed that way because the alternative, iron, was chemically much harder to get right. Iron actually appeared in human hands earlier than bronze. But it didn't come from the ground. It fell from the sky. Beads found at Girtse in Egypt, dating to around 3200 BCE, were examined in 2013 using scanning electron microscopy by a team including Thilo Raren. The beads contained high concentrations of nickel, a signature found almost exclusively in iron meteorites, not in iron ore mined from the earth. Ancient Egyptians were shaping metal that had traveled through space. The most famous case came later. Tutankhamun, buried around 1323 BCE, was entombed with an iron dagger of striking quality for its era. In 2016, a team led by Daniela Comelli analyzed the blade's composition and confirmed it too was meteoric. Its nickel and cobalt ratios matched known meteorites recovered from the region around the Red Sea. For centuries, iron and star metal were effectively the same substance to the people using it. Rare, otherworldly, and available only when the sky provided it. Smelting iron out of ordinary terrestrial ore required temperatures and techniques far beyond what bronze production demanded. That gap would take another 1,000 years to close. Except there was a problem far bigger than temperature. Iron melts at 1,538 degrees Celsius, hotter than any Bronze Age furnace could reach. So early smiths couldn't cast it. They hammered it again and again, from a rough, slag-filled lump into something usable. And at first it wasn't even better than bronze, just softer and prone to rust. Then, around 1200 BCE, the Late Bronze Age collapse hit. Hittite and Mycenaean palace civilizations fell within about 50 years. The tin trade that bronze depended on, routes stretching over 3,000 kilometers, broke apart. Bronze didn't get worse. It became unreachable. Iron ore, unlike tin, was everywhere. So smiths kept working it out of necessity, and in the process, kept feeding it into charcoal fires. Carbon from that charcoal slowly seeped into the iron's surface, a process called carburization, and produced something stronger than bronze had ever been: steel. Nobody understood the chemistry. They just repeated the ritual, and it worked. By 1000 BCE, that accident had a name: the Iron Age. Not chosen, forced, then perfected by trial. The metal nearest you right now carries that same chain. A stone that bent instead of breaking, a kiln that became a smelter, a collapse that made scarcity the mother of invention. It was never one genius. It was thousands of anonymous people noticing.